بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته أبنائي وبناتي طلبة الصف الثالث الثانوي لغات. نبتدي أو نكمل مع بعض دروس الكيمستري. The second lesson chapter 2, the electronic configuration and oxidation state. As you see in the table, the electronic configuration of the first transition series: scandium, titanium, vanadium, chromium to zinc. The electronic configuration of scandium 4s argon 4s2 3d1, and we are going to study this type of electronic configuration, which is called shorthand. Its oxidation state 3, group 3b. Some of the compounds scandium oxide. The oxidation state of scandium here 3 only. We are going to know why 3 only. Titanium argon 4s2 3d2. Oxidation state 2, 3, 4. The group 4b. Some compounds indicating the oxidation state TiO2, for example, titanium dioxide. Here titanium is positive 4, Ti2O3 positive 3, TiO positive 2. The Hund's rule in the electronic configuration of the electrons in D, 2 single electrons. Vanadium 4s2 3d3, 2, 3, oxidation state 2, 3, 4, 5, group 5b. These are some compounds, and according to Hund's rule 3 single electrons, and so on to zinc. There are some exceptions in the oxidation states, such as in chromium and in copper, and we are going to study them in the next pages. Let's go. Scandium, for example, 21, its electronic configuration 1s2, 2s2, 2b6, 3s2, 3b6, 4s2, 3d1. And the electronic configuration 1s2, 2, 3b6, this electronic configuration of argon. So we use argon instead of writing 1s2, 2s2, 2b6, 3s2, 3b6. Let's say we remove these sublevels and we replace them by argon. And after 3b6, 4s2, 3d1. And this is called shorthand electronic configuration. Shorthand صيغة مختصرة للإلكترونيك configuration, and we use it for expressing the electronic configuration for all elements and transition elements. But this formula argon 4s2, طبعا argon between brackets مربعة وبعدين نكمل 4s2 3d1. This expression considered wrong. What's the right? The right, it's called the electronic configuration of the outer shell. When we write the shorthand electronic configuration, we means electronic configuration of the outer shell. What is the outer shell? Which contain maximum principal quantum number. What's meant by that? Scandium will be argon 4s2 outside and 3d1 inside. Let's say 4s in the level 4 and 3d in the level 3. So it's written by this formula, and it will be the right expression for electronic configuration. Argon 4s2 3d1. And also this is the right, of course, electronic configuration, and also all other elements or electronic configuration of other elements. For example, titanium will be 4s2 3d2 and so on. Now in the fourth period, after calcium, there is a gradual filling of 3d sublevel, which is a first transition series. And 3d1 scandium, titanium 3d2, vanadium 3d3, and so on. by single electron. أول single electron in scandium, then till manganese 3d5, then pairing takes place till zinc 30 3d10 according to what's called Horn's rule. For example, scandium single electron 3d1, then gradual filling of the 3d orbital. Titanium 3d2, 2 single electrons. Vanadium 3d3, 3 single electrons. But in chromium there is exception, but also single electrons. One electron comes from 4s to 3d. Chromium 4s1 and manganese 4s2 3d5, 3d5. And after manganese the pairing takes place. In case of iron, Fe26 4s2 3d6, there are 4 single electrons and 1 pair electrons in D. After that, cobalt 4s2 3d7, another pairing, and nickel also 4s2 3d8, and copper will be 4s1 3d10, there is this exception, and the zinc will be 4s2 3d10. As you see in the table, the electronic configuration for S2 3d1 and its oxidation state positive 3. 3 means lose 2 electrons from 4s and 1 electron from D. Titanium, for example, its oxidation state 2, 3, 4. 2 means lose electrons of 4s2, and 3 means 1 electron from D. 4 means 2 electrons from S and 2 electrons from D, and so on. Let's say the lost electron first from 4s, then 3d, which are near each other in energy, as we are going to see in the next pages. Here, chromium and the copper have anomalous electronic configuration. Give reason. Chromium has the half-filled sublevels 3d5 and 4s1, and this gives it a kind of stability. How? Chromium, in case of scandium, d1, titanium, d2, vanadium, d3, chromium المفروض انه هو d4 و 4s2, but in case of chromium 1 electron transfers from 4s to 3d, and the 3d will be 5 electrons half filled لأنه filled by 10 electrons, and the 4s will be also half filled and filled by 2. Both of them are filled, and this gives it a kind of stability. So chromium has filled sublevel 3d5 and the 4s1, and the copper similar that copper has the filled sublevel 3d10 المفروض 3d9 بقى 10, and the half filled sublevel 4s1, يعني 1 electron from 4s transfers to 3d, so the atom will be more stable, less energy, more stable in these two cases. In case of copper, for example, argon 4s1 3d10. How? In case of nickel 3d8, as you see in the figure, but copper المفروض 3d9, يعني there is one single electron, but in case of copper, what happens? 1 electron transfer from 1s to 3d. It will be 3d10 and 4s1. So the atom will be more stable, less energy in these cases, in 3 cases. What are these cases? First, D0 means empty, and D5 half filled, and D10 filled sublevels. Examples of D0: scandium positive 3. In case of scandium, argon 4s2 3d1, and scandium positive 3, it will be argon 4s0 3d1. Thus say it loses 2 electrons from s and 1 electron from d, so d will be 0, more stable. Scandium will be more stable in case of the oxidation state positive 3. By the way, scandium has one oxidation state, which is positive 3 only. For this reason, it will be more stable. D is empty. Another example of D0: titanium positive 4. In case of titanium, argon 4s2 3d2. Titanium has 3 oxidation states. It may lose 2 electrons from 4s, and another electron from d, it will be positive 3, and the 2 electrons also from d, it will be positive 4 as shown. In case of titanium positive 4, it will be 4s0 and 3d0 will be more stable. So the oxidation state of titanium positive 4 more stable. And examples of D5 or half-filled: iron 3. Another example, manganese 2. In case of iron, argon 4s2 3d6. 4s2 3d6. In case of iron 2, lose 2 electron from s. Iron 3, the example that we have, it will lose 2 electrons from 2s and 1 electron from d. It will be 4s0 and 3d5. D5 means half filled, more stable. In case of manganese 4s2 3d5. Manganese 2 lose the 2 electrons of 4s, so the 3d5 more stable. In case of D10, the example is zinc 2 positive charges. Let's say in case of compounds, zinc shares or lose 2 electrons. Zinc 4s2 3d10. D is complete already. And in case of zinc positive 2, 4s0 lose the 2 electrons of 4s, and 3d remains, the 10 electrons in 3d remains without change, so it is complete, it's more stable. There is a note here: the filled or half-filled 3d sublevel is not only the main factor that causes the stability of the atoms. Let's say there are different reasons for stability rather than the half-filled or filled sublevels 3D. Next, give reason: iron 2 is easily oxidized to iron 3, while manganese 2 isn't easily oxidized to manganese 3. Let's start with iron. Fe argon 4s2 3d6. Iron 2 lose the 2 electrons of 4s, it will be 3d6. And by oxidation to iron 3 means you lose 1 electron. Iron 2 positive 2. Oxidation to iron 3, lose 1 electron. The 1 electron lost from 3d6, it will be 3d5. d5 more stable. Yeah, let's say iron 3 is more stable. Iron 3 is more stable as 3d sublevel is half filled. So the oxidation of iron 2 to iron 3 is easy. Again, why? Because iron 3 contains half filled 3d sublevel, which is more stable. In case of manganese 25, argon 4s2 3d5. And in case of manganese 2, let's say the 2 electrons of 4s is lost, and manganese 2 means 3d5. By oxidation, losing electrons. Manganese will be 3 positive 3 means it lose 1 electron from 3D. So 3D will be 4. In case of the 3D 4, not stable. But manganese 3D5, manganese 2, 3D5, more stable. So it is difficult to oxidize manganese 2 to manganese 3. Why? Manganese 2 contains half-filled 3D sublevel and it will be more stable. Number 5. The oxidation state increase from scandium to reach the maximum at manganese positive 7 in group 7, then decrease to reach positive 2 in zinc in group 2b. Next, as you see the table, scandium lose 3 electrons, the group 3. Titanium maximum oxidation state for group 4. Vanadium the group 5. Chromium group 6, manganese group 7, and in group 7 maximum oxidation state positive 7. And in case of iron, cobalt, and nickel, where they can't reach 7 oxidation state, they are in group 8. Copper, for example, copper is copper, silver, and gold. This group 1b, it is the only group in which the oxidation state becomes more than the number of the group. In case of zinc, group 2, group 2b, oxidation state 2, group oxidation state 2. The maximum oxidation state of any elements can't exceeds its group number except group 1b. Group 1b, as we said, copper, silver, and gold. Next, number 7, give reason we can't obtain scandium positive 4. We said that before. Scandium, argon 4s23d1. Let's say first energy level contain 2, second energy level contain 8, third energy level maybe 9, fourth energy level 2. It loses the 2 electrons of 4s and 1 electron from d. So its electronic configuration similar to argon 288. To obtain oxidation number positive 4, we break the level M, which contain 8 electrons. Scandium 4s03d0, scandium positive 3. But scandium positive 4, we break completely filled shell. This causes breaking a completely energy level, and the ionization energy is very high. As next, definition of the transition element. What's meant by transition element? It's the element in which the orbitals of d or f occupied with electrons but not completely filled in either the atomic state or in one of its oxidation state. One of its oxidation state means one of its compounds. That to say, يعني الترانزيشن element هو element اللي فيه D not complete or F not complete. We know that D, the elements that ended by D, is called main transition, and F inner transition. F D or F complete in both cases, elemental state and oxidation state, it is non-transition element. Example, give reason. Kinetogen metals, copper, silver, gold, are transition element, although they contain filled sublevel D in the elemental stage, as you see. copper 4s1 3d10, silver 5s1 4d10, gold 6s1 5d10. The answer: because in the oxidation states positive 2 means you lose one electron from S and one electron from D, D will be 9, يبقى not complete. And the positive 3, the sublevel D is partially filled, will be D9 or D8. Copper 2, yeah, what's meant by copper 2? For S0, lose one electron from S and one electron from D, D9. D9 يعني partially filled, not complete. Then copper will be transition element. Gold 3, Au3 positive means lose one electron from S and two electrons from D. D will be 8. D will be 8 means what? Means not complete, partially filled. So they are transition elements. Kinetogen metals are transition elements for this reason. Next, zinc, cadmium, mercury, these are in group 2b. Ns2 n-1 d10. This is the general electronic configuration of group 2b. Zinc, cadmium, mercury. And of course between them here F block. Case of mercury and cadmium. These elements are not transition elements. Why? Because the D sublevel is filled. D complete مليان في كل أحواله in the atomic state or in the oxidation state positive 2 لأن oxidation number بتاعهم positive 2 only, lose the 2 electrons, so they can't break the sublevel. It's more stable when it's complete, so they are called non-transition elements. This is the last